Welcome back, everyone. Today we're going to be looking at some applications of exponential functions. And just to recap what we were looking at yesterday, we said an exponential function was going to be something like y equals b to the x power. So you have some base to the x power. We said that base couldn't be 0, couldn't be 1, because that would create a linear function. So then we looked at something like y equals 2 to the x. And we made a table of values. We plugged in some negatives, some positives, some zeros, but in the table of values, right, let me put it this way, the negatives, they're not really going to apply. We're going to ignore the negatives here because in a contextual situation, that's what we're looking at, these word problems, we're not going to be dealing with anything negative. So everything is going to be happening in this first quadrant, right? So we can plug in the 0, the 1, the 2, the 3, and whatever else we want, right? If we plugged in 0, we said anything to the power of 0 was 1. So this graph started at 1, and so did all of the graphs that we were looking at there. So the function starts at 1, and then 2 to the first was 2, 2 squared was 4, 2 cubed was 8. And what's happening here is we're multiplying by 2, right? Because the base is 2, we're multiplying by 2. And I just want you to see that this is the factor that we're multiplying by to continue this list. And not only that is that the factor, but in front of the 2, we have technically a 1, right? That's like when we're looking at x squared, y equals x squared is the parent function. We know there's a 1 hiding there. And when we change the 1, we change the width of the graph. In this case, when we change the 1, what are we going to change? Well, we're going to change where the graph starts, right? If we have a 1 here, when we put the 0 in, right, that's where our graph starts, put the 0 in for x and it starts at 1. If I have a 1 there, 0 times 1 is y the graph starts at 1. Well, if I change this to, let's say, a 4, when I plug in the 0, well, 2 to the 0 is still 1. 1 times 4, though, would mean this graph would start way up here at 4. So this number out in front affects the width of the graph, but more specifically, it's going to tell us where the graph is going to start on the y-axis. And we're going to have to factor that in when we're looking at our exponential functions in context, okay? So we're going to be looking at an exponential function of the form y equals a times b to the x power. So not just some base with an exponent, that's a variable, but what's happening in front of that base is important here. So a is considered the starting point. That is, where do we start on the y-axis? Or if I plug a 0 in for x, right, what do I get back for my output for y? So where on the y-axis do we start? That's what we put in there for a. And then b is, we can talk about it two different ways. We can call it the growth factor or the decay factor. So what are we multiplying by to get from one number to the next? Now, let me go back to my scratch for a second. If I couldn't tell that, let's say 1 times 2 is 2 or 2 times 2 is 4, I could work backwards, right? I could take this y value and divide it, and 4 divided by 2 would tell me that factor was 2, just like we did with the geometric sequences, remember? So the rate of 2 here is like the rate of 2 here, and we would divide to work backwards if we had to. So if you're trying to figure out b and you're given 2 points, you take the second y value and you divide it by the first y value. So if you divide, you can figure out what that growth factor is, and that's again if you can't see it, okay? Now sometimes you're given a percent increase or a percent decrease. So if you think about your growth factor, remember we said the base couldn't be 1. So think about that growth factor as like a percentage, okay? Back to my scratch. So think about this as a percentage. 2 as a percent would be 200%. So when I go from here to here, going from 1 to 2, I have doubled my value, but the 1 is like the 100%, it's what I start with. Well, if I have 1 and 1 again, now I have 200% here. That is a 100% increase, okay? So if we're looking at b as a rate, a percent increase or decrease, we will always be starting at 100%, and then we add to that or we subtract from that depending on if we're increasing or decreasing. So to find b, if we're given a percent increase, you're going to add what percent you're given to 100. And if you want to find b and you're given a percent decrease, then you're going to subtract the percent decrease from 100. Okay, I don't know if it makes sense, but hopefully it will as we get to some examples here. So let's look here. The following graph shows the value of a car over time. Looking at the graph, not linear, right? We can see that that is an exponential curve, and it's asking us to write an exponential function to model this scenario. So we're trying to write something in this form, a times b to the x. So I need to know a, where does it start on the y-axis, and b, what are we multiplying by to go from the first y value to the second y value? Okay, just like our geometric sequences. So a is pretty simple. Where does it start on the y-axis? Right here. This car, this is the value of a car over time, has a $20,000 value to start. And then 1 year later, we can see the value is down to $18,500. So this is decreasing. That means that b has to be less than 1, right? We said yesterday, if it's bigger than 1, it's going to increase. If it's less than 1, it's going to decrease. So what are we multiplying by to go from 20% or 20,000 to 18,500 is kind of hard to see. So here, if I'm given these 2 points and I want to find b, I'm going to take the second y value and divide it by the first one. Take the 18,500 and divide it by 20,000. So 18,500 divided by 20,000 is 0.925, 0.925. So if you think about that as a percent, that means that from the starting year to 1 year later, the car is only worth 92.5% of what it was before. Okay, so that number less than 1 causes that decrease. Now, what is it decreasing by? Well, if we started, just so you can wrap your brain around this, if we started at 100% of the value, and now we're at 92.5% of the value, what have we lost? Well, we've lost 7.5% of the value. So we're losing 7.5% of the value per year, okay? So let me go back to this though. Our function for this scenario would be y equals 20,000 times 0.925 to the x power, where y is the value and x is the years. Okay, I guess we could have just put that here, x and y, but whatever, make sure you want to define your variables. So in part B, it says calculate the value. That means find the y in 5 years, means x is 5. So this is x is 5, we want to find y, so we'll just plug that in. So y is going to equal 20,000 times 0.925 to the 5th power. So calculator says 20,000 times 0.925 raised to the 5th power is $13,543. Calculator move. $13,543.74. So after 5 years, you've lost almost $7,000 of the value in your car. Now, part C says, when is the car going to be worth $10,000? So this time they're telling us y is 10,000, and we have to figure that out here. So if we plug in the 10,000 for y, 10,000 equals 20,000 times 0.925 to the x power. We have an exponential equation here that we have to solve. So we want to get that exponential part, the base of the exponent by itself. So the first thing we should do is divide over the 20,000. Now if we divide that 20,000 over, if I divide over 20,000, then this will cancel. And 10,000 divided by 20,000 is going to be a half. So we're left with 0.5 or half equal to 0.925 to the x power. And if you remember how to solve this, we're going to rewrite it in log form, right? If we want to look for a log is a power. It's going to tell us that power. So this becomes the log base 0.925 of 0.5 equal to x. So if we put in the log base 0.925 of 0.5, and we can see it's going to take about 8.89, let's see, about 9 years, okay? All right, now that is, I don't know, maybe more work than I would choose to do. I just want to show you how Desmos can help you do some of this work. Now I know it gave us the approximation there, but let me delete this all out. We said in the beginning, we created a function for this, y equals 20, oops, said equals, hit plus, 20,000, and then we were multiplying by 0.925 raised to the x power, and if we look, we should see, let's zoom really far, right? There's the same picture that we had basically happening on our paper, the same picture, okay? Now, just like with regression, we can use the model that's already graphed in here to try to figure out what's happening. So in part B, we wanted to know the y value when x is 5. Well, if I put x equals 5 in here and look at that intersection, it tells me that same value that I calculated by hand. Not that that was hard, right? But part C was a little tougher. If I, though, put in, same thing, y equals 10,000, y equals 10,000, and find that intersection, I can see 8.89, same answer I got, shows up on my graph. So if you can write the function, doing the work of solving doesn't really have to happen by hand. Is it something we should be able to do? Absolutely. But if you understand what you're doing on a graph, then that makes your life a whole lot easier, okay? All right, let's look at another one. So Mila paid $300 for a certain stock in January of 2008, and the value of the stock was expected to increase by 7.5% per year. So we're trying to write an exponential function to model that situation. So again, a times b to the x power. Well, a is no big deal. A, the starting value of the stock, 300. But b, we have to think a little bit. It says this stock is increasing by 7.5% per year. Now the value of the stock starts at 100%. If we add 7.5% to that, then what we're looking at is a 107.5% growth factor. So B is 107.5%, but as a decimal, that would be 1.075. So we're looking at a starting value of 300, and then 1.075 in there for B. And that number being bigger than 1 does show an increase. It will show growth of our function. If that was a percent decrease, we would subtract that percentage from 100. Okay? So now it says, and again, I didn't define my variables, but here y is the value and x is years. So calculate the value in 2020. So in 2020, calculate the value means find y in 2020. If this thing started in 2008, 2020 would be 12 years later. So x equals 12. So I've got two options. I can put my function into Desmos and then find the intersection with x equals 12, or I can plug 12 in by hand. I'm going to go ahead and graph this. It's just easier. So we have y equal to 300 times 1.075 raised to the x power. There's our function. Now what happens when x equals 12? What happens when x equals 12? That intersection says that when x is 12, our intersection at 12 and 714.534 tells me that the value is going to be about $714.53. Okay? And then in what year was the stock worth 900? This time they're giving me a value, a y of 900, and I have to find the x. So now I'm going to put in y equals 900 and find that intersection. And that intersection says, let's see, 15.191 900. That intersection says in about 15 years. So 15 years from 2008, which would, that would be what, 2023? The year 2023, okay? So for parts B and C, you could have done the same work we did for B and C on the first example, but if Desmos is there, right, makes your life a little easier, less places to make mistakes, by all means, use it. All right, so We have a few more types of examples. Here you're writing an exponential function from a situation. The next few that we're going to look at, we're actually going to be using a formula. So our function is given to us. We're just going to use it to do some solving. So here we have something that we often see in an exponential unit. This is called a compound interest formula. I don't know if you're familiar with compound interest, but basically it's like you're taking money out as a loan or you're putting money in as an investment, and you are either charged interest on your loan or you're earning interest on your investment. And with compound interest, every time your interest is compounded, it gets factored into how much you put in. So you have something called simple interest. I don't know if you've seen this formula before. Simple interest, principal times rate times time. If you put some principal amount into an account at some rate for a certain amount of time, you calculate interest once. There's some fee or some amount that you earn on your investment, right? Now with compound interest, instead of calculating the interest one time, you might do it, I don't know, quarterly or monthly or annually, whatever it is. Let's say it was quarterly. Quarterly would mean 4 times per year. That means after 3 months, you're going to calculate interest, and that interest gets added into your account so that for the next round, not only are you going to earn interest on the amount that you put in, but you're also going to earn interest on interest, okay? So don't get too hung up on the concept. That's sort of a general idea, but compound interest is basically you earning interest on interest. So either earning more interest on interest for investment or being charged more interest on interest for a loan, which would be terrible. But A in the formula represents the total final amount that you have earned or are being charged, depending on if it's an investment or a loan. P represents the principal, which is the starting amount, the original amount of money. R is the rate, and the rate's given to us as a percent, but we would plug it in as a decimal. T is a time, and it has to be in years. T is time in years. And then N is the number of times the interest is compounded. So if it said compound interest monthly, that would mean 12 times per year, so N would equal 12. If it was daily would be 365 days in a year, or quarterly would be 4 times for the year. What else could we put? Weekly would be 52 times for the year. What am I missing? Semi-annually, twice for the year. Annually, once for the year. Okay, so that's the idea behind that. So number 3, suppose you invest $4,000 at 8.25% compounded semi-annually. How much you're going to have total after 5 years? So we have a principal amount of $4,000. We have a rate of 8.25%, and that's going to go in as 0.0825, the decimal. Compounded semi-annually means N is 2 times per year. Right, semi-annually is where I got the N equals 2. And then how much you're going to have after 5 years, so T is 5. So finding that total accumulated amount means we're looking for A, which means we're not doing any solving here because A is already by itself in our formula. So 4,000 times 1 plus R over N, so 0.0825 over 2, and then raised to the NT power, so 2 times 5 power. So that final amount's going to be, calculator says, 1 plus 0.0825 over, oops, plus, oh my gosh. Point, geez, 0.825. Calculator problems. Sorry, guys. Okay, then we're going to raise that to the, if you want both numbers to be in the exponent, you're going to put parentheses, so it's N times T, 2 times 5, or you could have just put it on a 10. So we end up with, at the end of the 5 years, $5,992.53. And since you started with only $4,000, that's almost $2,000 in interest, okay? It's not so bad, and actually a pretty simple problem, but since this is in our unit, the goal would be not to always just be finding the total final amount there. It would be to, solve for one of the exponents. Solve for n, solve for t, solve for whatever. So let's look at this next example. Next example, suppose you invest $7,000. 30 years later, you have $24,789 in the account, and the interest rate was compounded semi-annually. What is that interest rate? All right, so this time, 7,000 principal amount. 30 years later, T is 30. You have 24,789. That's the final amount, 24,789. And interest is compounded semi-annually, so again, n equals 2. This time we're trying to find the rate. So the rate is the question, right? The rate, let's leave this blue. The rate is the question, so that's going to be the piece that stays in a variable. Here it was, how much will you have total? That was our question there. That was why we were looking for A. So this was A as the question. This is R as the question. So let's plug in what we have. We have 24,789 equal to principal 7,000, and then 1 plus some rate over 2 raised to the nt power, so 2 times 30th power. Yikes. How do we solve this thing for R? I would say let's get rid of the 7,000 first. Let's divide both sides by 7,000. Makes that go away. Now if this is an ugly decimal, non-repeating, non-terminating, then I'm just going to leave it in as a fraction. If it's not so bad, yeah, I'm going to leave that as a fraction. I don't want to have to round this twice in a problem, or round more than once, so I'm going to leave in this fraction here. 24,789 over 7,000 is equal to, we've got 1 plus r over n to the 2 times 30 is the 60th power. So r, n was 2. R is trapped in the parentheses there. I can't get rid of that divide 2 or that plus 1 until I get rid of that 60th power. So how do we get rid of the 60th power? Let me ask you this. If there was an r over 2 and let's say a plus 1 and it was being squared, how would we get rid of the square? We would take the square root, right? If it was a cube, we would take the cube root. If it was a 4th power, we'd take the 4th root. So if it's a 60th power, what do? We take the 60th root. Okay, we're going to take the 60th root of both sides, which seems crazy, but that's doable. So that's going to give us, on this side, we're going to leave this craziness, 60th root of this fraction. I know that's going to be some decimal, and I don't want to round it till the very end. It's going to equal 1 plus r over 2. So now to get r by itself, I'm just going to subtract the 1. So if I go here, it's going to be the 60th root of the 24,789 over 7,000 minus 1 equal to r over 2. And then I have to multiply both sides by 2 to get rid of that division. So it's 2 times the 60th root, 24,789 over 7,000 minus 1 equal to r. And that is a big mess there, but the calculator is going to handle it. So we said, let's see, the 60th root of 24,789 over 7,000. And then from that, outside of the radical, make sure you're outside of the radical, we were going to subtract 1. And then that whole thing had to be multiplied by 2. And that gives us 0.0426-ish for r. So we're looking at about 4.26% for that rate. And that was significantly more challenging than the other problem because we had to solve for something different. But hopefully work, that makes sense, we've seen before. Okay? Let's try the next one. Next one says, how many years is it going to take for an investment of $25,000 to grow to $80,000 if it's invested at 4% compounded monthly? So the initial investment, $25,000 is P. We're trying to get that to grow to $80,000, so a final amount A of $80,000, and it's invested at 4%. Rate is 4%, which is 0.04 as a decimal. Interest is compounded monthly. That tells me N is 12. And this time we want to know how long. How many years means this time T is our question. T is the question. So we have 80,000 equal to 25,000 times 1 plus r over n raised to the nt power, so 12t power. So we're going to try to solve for t in this one. Let's still begin by getting rid of that 25,000. That cancels. Let's see how bad of a decimal this is. 80 divided by 25. 3.2? Yeah, that's manageable. So let's make this 3.2 equal to, I think we can condense what's going on in the parentheses there too. 1 plus 0.04 over 12. I don't want to round that off either, so okay, I'm going to leave this. 1 plus 0.04 over 12. That is raised to the 12t power. 12t. So on this one, we have to solve a little differently. This time we're looking for our variable is not stuck in parentheses. Our variable is our exponent. This is an exponential equation. So how do we find that exponent? We use a log. So I'm going to take this and rewrite it in log form. This becomes the log base, this crap, 1 plus 0.04 over 12 of 3.2, and that's equal to 12t. Now if I want to solve for t, I just have to divide over the 12. Divide that mess by 12, so t is going to be approximately, let's see about getting this into the calculator. Make a fraction first, so it's going to be the log, and the base of the log is, oof, I don't know if it's going to let me put 1. Try this again. 1 plus 0.04 over 12. Nope. Let me fix this again. Let's see. 1 plus 0.04 over 12. Let's 301 over 300. Let's try. Log base 301 over. No, that's not what I want. Log, just like some playing with the calculator. Nope. Okay, maybe we have to round this off. 1.0033. It's probably going to be close enough to our answer. So we're going to make this log base 1.0033, however many threes you want, whatever, of 3.2. Let's see if I take away some threes, how different is our answer? Oof. All right, let's put some of those threes back in. And this whole thing had to be divided by 12. So we're looking at 29.13-ish. So 29.13-ish years. So notice I struggled a little bit to put that mess in the calculator. In the calculator, I had to put this in as 1.00333. I hate to have to round before I get to my final answer, but obviously I couldn't figure out how to put that in the calculator without doing that. So, play with the calculator. If you figure out a way, maybe you can let me know. All right. We have one last formula to look at, basically the same thing we're doing here, but instead of interest being compounded monthly or quarterly or whatever it is, we're going to look at interest that is compounded continuously. So with no time intervals, just compound continuously. And this uses a formula where E, our Euler's number, is the base of our exponent. So we have the P, the RT, that part is the same, but instead of 1 plus R over N in the parentheses, we have an E as the base of our exponent. So again, this is, we could see this in financial situations, but usually it's like continuous growth or decay in like a science-based situation, like you have maybe a bacteria that grows exponentially, or like a coronavirus that is growing exponentially. In that case, you would use, we call this PERT for obvious reasons, I think. We would use this continuous growth formula to calculate a final amount or a starting amount or a time or a rate. So A is still the total final amount, and I don't want pink in there. Total final amount, so that's the same. P is the principal, the original or starting amount. And then R is still the rate, which we would convert. And then T is still the time. Okay, so same components, just a different base for our exponents. So we have in number 6, an investment of $300 made into an account that compounds interest continuously. So when it says compounds continuously, not semi-annually, monthly, annually, one of those other words, so we know exactly how many times. If it's continuously, you're going to use this formula. At a rate of 1.5% for 4 years, what is the final value? There's our question. The final value, that's telling us look for A. Right, what is A in this one? So we know that the principal is 300. We know that the rate is 1.5%, which is 0.015 as a decimal. And we know that the time for this investment is 4 years. So A is going to equal 300 times E to the 0.015 times 4 power. So let's calculator from there. 300 keyboard E raised to the, in parentheses, 0.015 times 4 is $318.55. $318.55. Since we started with 300, that's at $18.55. $18.55 earned in interest. Okay, obviously not the goal necessarily for this unit. We're going to be trying to solve for R or T. So it says, suppose the start of an experiment in a biology, or at the start of an experiment in a biology lab, there's 1,200 bacteria present in a colony, and the population grows continuously for 4 hours, bringing the population to 2,200. Let's figure out the growth rate. So we're trying to figure out the R in the formula. Sorry, lost my head for a sec. So we know that the principal amount of bacteria, the starting amount of bacteria is 1,200. We know the final amount of bacteria is 2,200. We know that this happens in a time of 4 hours, but we don't know R. That's why it's asking us to calculate R. So we have A, which is 2,200, equal to P times E to the RT power. So R times 4 power. So now when we solve this here, right, the last one we didn't have to solve. A was already by itself, but now we have to solve for R, and that's an exponent, which means we're going to have to use logs. But let's divide this 1,200 over first. Let's get rid of that piece. So we can clean up the 2,200 over 1,200. And I don't want to make it a decimal, but 11/6 would be a little easier to manage. So I'm going to make this 11/6 over here, and equal to E to the R times 4 is going to be 4R power. So I'm looking for an exponent, I'm going to use a log. Now because this is a base of E, I'm going to use the natural log when I rewrite. So when I rewrite this, it's going to be the natural log base E, which it already is, of 11/6 equal to 4R. So now I just got to divide by 4 and then go to the calculator. So R is going to be exactly, natural log is already base E, so I don't technically have to write that there. So let's see. Natural log of 11/6, and that's going to be divided by 4. So we're looking at R is, oh my gosh, R is approximately 0.152-ish. 152-ish, so this is about 15.2%. Okay, that is our growth rate, 15.2%. So now it says how many bacteria were there 3 hours after the population begins. So now that we have R, we technically have a formula for this situation. The formula says that any final amount, right, is going to be 1200 times e to the r we calculated at 0.152, so it's 0.152 times t. So this would be like the particular equation for this scenario, where the beginning amount of 1200 isn't going to change, and that rate isn't going to change, right? But time could vary, and the final amount could vary based on that time. So now, how many bacteria were there 3 hours after the experiment begins? Tells me to plug 3 in for t. So what is the final amount when we put 3 in there for t? So let's find out. Let's see, 1200, keyboard, e, and then we're going to raise that to the 0.152 times 3 power. So we have 1893.3. 1893.3, but this is a final amount of bacteria. You're not going to have 0.3 of a bacteria, so we're going to say about 1,893 bacteria. Okay, and then lastly, it says when is the population going to reach 3,000? So we know the final amount we're looking for is 3,000. And that's 1200 times e to the 0.152 t is what we're looking for in this one. So again, we're going to be trying to solve for an exponent here. So we're going to divide the 1200 over, cancel that out, 3000 over 1200, 2.5, that's much nicer to write. So let's make this 2.5 equal to e to the 0.152 t. Now I can rewrite this in log form. Since I'm looking for an exponent, I'm going to use a log, and natural log because it's base e. So natural log, already base e of 2.5 is going to equal 0.152t. So now I just have to divide over that 0.152, and I'm done. 0.152, that's gone. So t is going to be approximately natural log of 2.5 divided by 0.152. 6.028. 6.028, so a little over 6. This is not years. What is this here? These are hours, right? Yeah, this is time in hours, so a little over 6.0, let's just say a little over 6 hours. And there it is. Okay.